Welcome to Monochemistry. Today we're going to look at a practice problem, dealing with the common ion effect. And here's the question. Part A says to calculate the pH of a 0.20 molar solution of acetic acid. Part B says to compare this pH to that of a mixture of solutions of 0.20 molar acetic acid and 0.30 molar sodium acetate. So when I get a problem like this, I like to just I might not actually draw it out, but it's a good idea for the first few times to draw it out. But I might just draw out a couple of beakers here. One representing just the acetic acid solution, and the other one representing the mixture. Okay, so you've probably already noticed that acetic acid is a weak acid. Okay, so its dissociation is really low. And so therefore, inside a beaker filled with water, I'm going to have mostly these guys. And very few of those. Now in this other beaker, I've added a very soluble salt called sodium acetate. Now how do I know that's very soluble, you ask? Well, you guys should know, because it's a group 1 metal compound. So therefore, it's completely soluble. So I know that it's completely going to dissociate. Now here's the thing. All things being equal, so assuming that I have all of that in this solution as well, what's going to happen here is that, notice, there's extra of this. And I've also got this H plus floating around. So what are these two things going to do with each other? Well, this and this are going to react with respect to Le Chatelier's principle, and they're going to reform CH3COOH. Okay, so you've got Le Chatelier's principle acting out here. So what that means is that the pH of this solution, because of the H plus concentration, is going to be lower. It's going to have a lower pH. And this solution over here should have a higher pH because there's less H plus in solution. Let's see if we get that as our answer. Let's go ahead and start by solving for the pH of a 0.20 molar acetic acid. Okay, so part A, we're going to use the Ka of the acetic acid. Remember, these are equilibrium constants, so we're going to use ice tables here. The good news about these ice tables is that the X value is almost always, like 95% of the time, the X value is insignificant compared to the actual value of the molarity or the concentration of the original substance. So in other words, it's never going to be a quadratic. Okay, so we use the Ka of the acetic acid and the ice table to solve for the pH of the acetic acid. Remember, pH is minus the log of the H plus. So once we solve for X, we know the H plus concentration, we can find the pH. Okay? So remember that the Ka of this particular thing is going to be equal to the concentration of CH3COO minus times the concentration of H plus divided by the concentration of CH3COOH. Okay? Now substituting in the values, and I'm not going to show all the work here, I'm just going to give you a final answer. Substituting in the values, notice I've given you the Ka right there. So 1.8 times 10 to the negative 5 is going to equal all this stuff. I'm going to go ahead and solve for this particular thing. Okay? And I'm going to tell you what x equals here in a second. So, if you don't want to hear the answer, you want to solve for it, you better hit pause and work it out yourself. You should be working this out yourself. Okay, so x equals, with significant figures, 1.9 times 10 to the negative 3. Now I'm going to tell you what the pH equals. Remember, pH is minus the log of the H plus concentration, which is what this is equal to. Okay, so again, you solve it yourselves, but the pH is equal to 2.7. 2.7. Okay, with the significant figures given in this question. Alright, so that is how you solve for the pH. Now we're going to use the other. We're going to do B, and we're going to solve for the pH of that solution. So let's go over and figure out how to do that. Alright, so there's a couple of things to keep in mind in this. This problem isn't a whole lot different than the previous one, except for the fact that we've got a mixture of solutions. And therefore, because of that mixture of solutions, we've actually got a couple of things going on here that are a little bit different. Not a whole lot, but a little bit. Okay, so remember, this is the salt. It's the CH3, the sodium acetate, sorry, and its initial concentration was 0.30 molar. Now, it dissociated into acetate and sodium. Because it's completely soluble, we assume that the values, the initial concentration will equal the equilibrium concentrations of these guys here. And it's not really an equilibrium because it just goes. Okay, now what does that mean? Well, let's go back over here. We know that the initial concentration of the acetic acid was 0.20. But because we already had this guy here in solution, notice that the initial concentration of CH3COO- is actually going to be 0.30. And the H plus is going to be 0 initially. Okay? So we have our equilibrium concentrations of these things being right here. Now again, just like in the previous problem, the X value is so small that it's not going to be important to use in our overall expression. So we would assume, in this case, that the Ka, which by the way is the concentration of this times this divided by this, just like last time, the Ka is going to be equal to 0.30 times X divided by 0.20, which of course equals 1.8 times 10 to the negative 5, which I gave you last time. Okay, so even easier to solve for X this time, and then calculate the pH. So I'm going to put it on, I'm going to give you a second here to put it on pause. I'm going to go ahead and I'm going to tell you what the answer to X is and the pH, but you guys need to do it yourselves right now. Okay, so X equals 1.2 times 10 to the negative 5 molar, which of course also equals the concentration of H plus, which is very important. Okay, so now we're going to calculate the pH. You go ahead and do that on your own, and I'll tell you what the answer is after you unpause it. Alright, and the survey says that the answer is 4.9. Now, if you think back to what we originally predicted, we predicted that our acetic acid solution by itself would have a lower pH than the acetic acid mixture with the sodium acetate. And we were right. Way to go, Lechat, because we were right. Alright, and that's how you use the common ion effect to solve for pHs of solutions. Now, I'm going to show you another trick right here. Here's the good news. As I mentioned in the previous video, there is an equation called the Henderson-Hasselbalch equation. And that equation can be used without ice tables to solve for this particular question. Okay? So our mixture of solutions are sodium acetate and acetic acid. Plug the numbers into this equation and you should get the same answer. I want you to try it. Okay? Remember that pKa is going to equal minus the log of the Ka. We already know that the concentration of A minus is 0.30 and the concentration of HA is 0.20. Plug those numbers in and tell me you don't get the same answer of 4.9. That in a nutshell is how you use these equations and these types of, this is how you use this equation and also how you use the ICE method to solve for common ion effect practice problems.